Okay, good morning everybody. Hope everything is okay for you. In the name of Allah, starting the lecture. If you have any questions, let me know before I go to the next lecture. We go first to the lecture and then we go to see your reflection also, and also talking about the midterm exam. Okay. So, where were we? We were talking about Carnot map, how to use Carnot map to simplify logic functions, and we had seen 2-variable Carnot map, 3-variable Carnot map, 4-variable Carnot map, and somehow the 5-variable Carnot map also. We had one example from 5-variable. Then we were talking about don't care. There are situations that you don't care you don't care for the output for a number of inputs. So whatever input those inputs are, you don't care about the output. It could be 0 or it could be 1, and it doesn't matter. So we've talked about that, and this was the last example that we have done. Why it's not going to? Oh, okay. So here again, for don't care examples, we were trying to group the cells as much as possible to make bigger groups, and then we select our essential prime implicants based on the one, not don't cares, and then if anyone is left, then we pick the other prime implicant. So let's, for example, here we have here something, we have here, if we consider don't care as one, then you can group them together. Then what else? I guess we could group this with that. And is there anything? No, that's it. That's it. Yes.
You could have the horizontal line CD.
Okay. Horizontal line CD. Oh yeah, you are right. So even. So I shouldn't have put these two together. The 4 could be together. Okay, so I have to correct it. These 2 is not good. The 4 is good. Yeah, these are good. Yeah. So it seems that we have 3 prime implicants. All of them has 4 members, 4 cells. Now let's select the essential ones. If you look at the vertical one has this one as essential. It has this one which makes it essential. This one is not in any other implicant. The square one has this one. Which makes it essential, and the horizontal one has this one. So all of the 3 are essential, so it's very easy. We just put this one, and okay, we could have picked another one that I didn't. We could have picked this one also as an implicant, because at the beginning we try to make as much as big groups we could select. So we should have select this one also. But it doesn't have any 1, so it is not coming into our essential prime implicants. And it seems that after we select our 3 ones, we don't need that. So that our function has 3 terms. 2 one and green one. Any questions? So that's what we have already covered in the last session. Now let's go to, this was also, we didn't detect that one also. So we could use that, and this is another prime empty. Now we go to mix terms. You know what is min terms, yeah? Min term is the product term which has all of the variables. For example, if we have 3 inputs, we have A, B, C, then A prime, B, C prime is a min term. Max term is the dual of that. We have talked about dual before, and is dual of OR. De Morgan rule says that inverting an AND becomes an OR, and so we had so many things before. Now we are saying max term. So for the duality, what do you guess about max term? What is a max term?
It has only like one of the fewest amount of
It has?
variables.
It has what?
One of the fewest amount of variables.
No, like min terms. Min terms has all the variables with product. So max term has also all variables, but sums. Yeah, sums. So it should be sum. So for example, look at this one. With this example, I explain the idea, and then we will define it later. Look at this function. Up to now, we look at this is W. This is W. We look at ones and select them either in Carnot map or in sum of products, and then we try to simplify. So here we have sum of products of 1, 3, 4, 5, and 7. So W is the sum of products of min terms 1, 3, 4, 5, 7. 5 min terms. They are min terms, which correspond to, for example, these correspond to what? A naught, B naught, C. And then we sum, we OR all of them together, and we have our function. Okay? Any questions here? Clear? Okay. Now, in this function, we could see that there are 5 1s and 3 zeros. So maybe if we go for the zeros, that would be easier, because it has only 3 min terms, three terms. So we look at W bar. If you look at W bar, so wherever W is 0, W bar is 1, and vice versa. Whenever it is 1, it is 0. So if you write the truth table for W bar, it has 3 1s and 5 zeros. Yes? Okay? So now let's do what we have learned before. Selecting the ones and trying to make a product, a sum of product, and either using a Carnot map, which I will link it for you in the next slide, or trying to simplify. Okay, so writing the expression for W bar is easier here because it has 3 terms. The W has 5 terms. And we could write it for you. W bar, so let me clear this. W bar has 3 min terms. So we could write it. W bar is this, which is A naught, B naught, C naught, and then this, which is A naught, B, C naught, and also number 6, which is A, B, C naught. Okay? This is W bar. Now you want to have W, so invert it, negate it. So W bar W bar bar. W bar bar means inverting this. Inverting this based on the De Morgan rules will be inverting each one of them with and in between. So let me write it for you. Inverting A naught, B naught, C naught, and A naught, B, C naught, and A, B, C naught, naught. Okay? So inverting all of them. Now, now inverting this A naught, B naught, A naught, B naught, C naught. Why didn't I put that one? So inverting this again with De Morgan rules becomes inverting of each element, but plus or between, not and. So it becomes A plus B plus C. Then we have and here, so and comes here. Then we have this one. This one, A naught, B, C naught. Inverting that becomes A, invert of that, B naught, C, but with OR. And then the last one is A, B, C naught. A becomes A naught, B becomes B naught, C naught becomes C. So again, here you see we have three terms, but this time our terms are sum, are OR. Last time our terms were min terms and they were product terms. Here our terms are sum terms and we are ANDing them together. So here we have product of sums. Instead of sum of products, we have product of sums, and we could write it with the pi as a product terms with the numbers. The numbers are 0 to 6. So number 0 to 6 correspond to Mach term, and that Mach term is or of the three elements A, B, C, depending on which cell we are. For example, here they are A plus B plus C. Be careful. When this has 0, 0, 0, for Mach term we write A, B, C. For min term we had written A naught dot B naught dot C naught. Here we write A plus B plus C. And you know why? Because if you look at, let's say, a truth table, let me put a very simple truth table, two variables, A, B in F. So 0, 0, 0, 1, 1, 0, 1, 1. So if you look at them, and F is 0 here and 0 here, for example, and 1 here, then as we talked before about the product terms, here we could talk about the sum terms. We can represent this 0 by A plus B, and A plus B is something which is something with this truth table. Let me show you what is the truth table of A plus B, which you know for sure. A plus B is this one. A plus B, 0, 1, 1, 1. And then this 0 corresponds to A naught plus B naught. A naught plus B naught has 1, 1, 1, 0. Okay? A naught plus B1 is 0, 0, 0, 1, 1, 1, 0. Now you have two columns. One of them is 0 in one place and 1 in the rest. So if you AND them together, if you AND this together, you will reach this. That's this is the same thing that we have talked before. We wrote the product terms and then we said, okay, if you OR them together, each term brings you a 1, so you have formed your function. Here we say each term brings you a 0 of the function, and then you AND them together. That would be okay. Yes?
Why do we get 0 to 6 for W?
Okay, for W, the max term are 0 to 6. The min terms are 1, 3, 4, 5, 7. But the max term are 0 to 6 because
Is that what the M, like the M is like
capital M. Capital M is max term, small m is min term. I am saying midterm because you have midterm. Yes.
Because the values for non-W, like 0 to 6.
This is when we wanted to explain, but you could not think about that. You just could think about directly about the max terms, because W, as I explained here, W is 0 in 2 positions and 1 in 2 positions. The same thing that you mentioned, you mentioned about the midterms, the min terms, that you put them and then you OR them together. Again, the same thinking would be here, that you select the zeros and put them as OR, and then you AND them together. The same thing. So you don't need now to think about the min term, then think about W naught, and just that was for explanation, that you could see that W naught you could express it using min terms. So W you could express it using max terms, and they are the same. And again, remember, this is M as the max terms, and max terms 0 to 6. The rows that have 0, they are max terms. We could do the same thing for Carnot-map. First, I try to use the concept of W bar, and then we go directly to W and try to use Carnot-map for max terms. Why do we use W bar? So the same function that we had before, this is W bar. W bar had 3 1s and 5 zeros. This is the same function that we had before. So again, for Carnot-map, you start making the maps. So this is 1, this is 1. What else? That's it. Yeah, that's it. You have 2 implicants here. So the function would be very easy, and it would be this. And again, the function would be this, A naught C naught, which is this one. Let me clear. So it is A naught C naught, which is this one, A naught C naught, and the other one, which is B C naught. But this was W bar. For finding W, we have to invert it. So we had put a bar here, and this becomes bar are each one, but instead of OR, they have AND. Then each one would be this. So you see, we used Carnot-map for simplifying W bar, and after finding W bar, we inverted and became this. Here you see we have 2 terms, 2 sum terms here, and with a product. So product of sums we have here. And as we talked before, they are not max terms, they are terms. They are actually a simplified terms, not the max term. Max term should have all the variables, A, B, C. This is a simplified version. Okay, but as I told you, we could directly use the map for W. So this is the map for W. It has 3 zeros, 5 1s. Why not trying to use whatever we said before about the 1, mapping the 1s, now use it for 0. mapping zeros, exactly with the same concept. Adjacent cells, we try to group them together, the adjacent cells, and then write a term for that. Okay, here again we see that we have two implicants. Here we don't say it implicants, so to make it to differentiate it, we say implicate. So we have two implicates here, not implicants, but two prime implicates. Which one is essential? Both of them, because this one has this and that one has this. So both of them are essential, so we pick both of them, but remember, they are zeros. So we should write Marx terms for that. The first one, this one would become what? This one would become A plus C. Pay attention. That one would be A because this is A. In previous examples, this one was A naught, that one was A. Here, this one is A, this one is A naught. This one is C, this one is C naught. And this is B naught, and those two are B. So this would become A plus C, and this one would become B plus C. So this one A plus C, B naught, well, sorry, B naught. This is B naught. Okay? Directly, without using W bar and then using min terms, just Marx terms, and then we know what to do. Okay? Yes?
Wait, so why did we say A plus C if it's A not?
A plus C in Marx terms means this. A plus C. Yeah? Yes, dual. Don't say dual. It is the dual of what we have told before. There we had 1, here we have 0. There we have A naught, we have A here. And you knew the concept, what was the reason, because in Marx terms, we are selecting zeros. And for zeros, we try to make a term which will be 0 at that position and 1 for the rest of the rows. And that would be A plus C for that position. Okay. Another Marx term example. Okay, it would be easy. You know how. Here actually zeros are more than ones, but what we want to do as a Marx term example. Again, we try to map them to find the implicates. This would be one implicate. This is another one. This is another implicate. Okay, this is also an implicate. You remember the wrapping is also here because they are adjacent. So you could pick these two together. Any more? I picked 4. Do you see any more? I don't think so. So which one are essential? So let's highlight them. The essential ones. So this is essential because of that. Oh, why it's not working? Oh, what happens? Highlighter, and so I select, let's say, blue. Yeah, for that one would be essential. This is not essential because it has covered with something. This one has a term which is not covered by any other, and this one is covered here. This one is, so that's it. We have 2 essentials. We have 2 essentials. So let's write them. This one. Here you look at this. This this one would be A plus C naught, okay? A plus C naught. So this is A plus C naught. And what was the other essential? This was another essential, and that essential would be A naught plus C. So what we covered this. So 1 0 is left, and we have 2 implicates. Yes, please.
Sort of curious, in this case, wouldn't it have been easier to just use min terms?
Yes, because there are three ones. Yeah, just for the sake of example, we wanted to. Yeah. So we have 1 0 is left, and we have 2 implicates. We could select either one, whatever you want to select. Yes. A naught plus P. So you selected this one. This one, yes. Or you could select this one, which would be B plus C naught. Yeah. So whatever you pick up. So this and these, they are essentials, and it's already there, but you could use this or that one. So that would be here, we selected, we picked up A naught plus B, but you could pick up the other one. If you want to write it as max term, so you could write it here. You see we have 0, let me put the numbers on that. 0, 1, 2, 3, 4, 5, 6, 7. So we have zeros of 1, 3, 1, 3, 4, 5, and 6. The zeros are 1, 3, 4, 5, and 6. This is the marks terms. Okay. Any questions? Now we are going to our last maybe topic in the logic minimization, which would be our last topic in midterm. So your midterm is at the end of this topic. So whatever I tell you later, it is in the final exam, not in the midterm. Okay, we want to talk about timing a little. Up to now, we just assumed that everything is very instantaneous. Whenever you have an AND gate, so this is A, this is B, this is C, and then, for example, you have A, B, and the output C. So you have, for example, A is 1 in this time. This is the timing diagram that we are seeing, like what you do in your simulations. If A is 1 at that time and B is 0 here, so C would be A and 1 and 0 would be 0. Then B becomes 1 here at this time, and A still is 1. So at this time, which I could, for example, put it here. So at this time, B is 1, A is 1, so C would be 1 also. C becomes 1 here. So let's say at this time, A becomes 0. A becomes 0, but B still is 1. Then at this time, C becomes what? At this time, C becomes 0 again. Bit red. I had a pen writing with that. I lost it. Have you ever seen that? If you have seen that, let me know. Okay. So this is the timing diagram. Okay. As soon as something changed in input, we assume that it instantaneously affects the output. Okay. Up to now, we were thinking like that. Everybody, okay? But this is not true, because each gate has some delays. It is not true. For example, to make it simple, we can say the AND gate has a delay of 5 nanoseconds, for example. 5 nanosecond delay. So if this is the case, now let's redraw the diagram with green. So at this time, A is 1, B is 1, so A is 1, B is 0, so C is 0. Still C is 0. At the first time, let's say T0. At T0, B becomes 1. B becomes 1. So it is not just momentarily, instantaneously, that C becomes 1. C becomes 1 with how much delay? 5. I said 5. This is an example. So whatever. 5 nanosecond. So after 5 nanosecond, C becomes 1. This is 5 nanoseconds. After 5 nanoseconds, C becomes 1, and it is 1. And then later in T1, A becomes 0. A becomes 0, so it means that not at that time it gets 0. It takes a delay, which is 5 nanoseconds. So again, 5 nanoseconds later, C becomes 0. So this is the true one. Actually, this is not the whole truth. The whole truth is different. But to make it simple, we just used a value for the delay and using like that. But the truth is that the delay from 0 to 1 is different than the delay from 1 to 0. But we don't go to that detail. If we were using gate transistor level design, then we could talk about that, which I will give you just a very brief introduction about that. But for us, we just use gate level delays and assume that this is the delay that any changes in the inputs will appear in the output after this delay. Any changes will be in effect after this delay. Okay, so let's see what's happening. Just to give you an introduction, I give you some electronic background. I don't know which one of you is in electrical engineering and knows about transistors. Anybody? Transistors? Which course did you have?
Oh, no, just from like personal.
From personal, yeah. So no course, no? No course for transistors? No? What about RC circuits? RC, for example, we have a power supply with a resistor and a capacitor. Did you analyze this? No? Ah, too bad. Yeah, this is the problem of computer science, because we say that we don't need these things, we just go to the higher levels, which is correct, but it is good to have some idea. So here I just give you some ideas. I am not asking about these things in exam, and they are not in your course, but it's good that you know these things a little. But let me show you how do we build gates using transistors. The building elements of gates are transistors. And the building elements of transistors are silicon. You use silicon, put some kind of electron and holes, because electrons has negative negative charge, and holes, which is the lack of electrons, has positive charge. But here we see a transistor for you. We just show you the inverter gate, which is the basic of all of the gates which we build, inverter. For inverter, we use such a circuit. This is the circuit for inverter. As you could see, in CMOS technology, CMOS, complementary MOS, metal oxide silicon. So CMOS technology, if you want to Google later, that's not bad. If you just Google, see what is CMOS technology and how do we build transistors and so on. So these are two transistors which complement each other. So we call this CMOS, complementary. And this transistor is PMOS, and this transistor is NMOS. Somehow negative, somehow positive. PMOS and NMOS. And how does this work? The transistor has some kind of switching performance. A PMOS, and each transistor has three pins, three gates. One of them we call it gate, the other we call it source, the other one we call it drain. So if each transistor has three pins. So here again, for our NMOS transistor, we have source, we have drain, we have gate. I guess it's recording. Okay. In PMOS, if you put a 0 voltage of gate to S, yes.
I'm wondering, what does VDD?
VDD is the power supply. Let's say it is 5 volts. And this is ground, which corresponds to 0 volts. Okay? So VDD is the power supply. I guess you should use VDD in your simulation in the lab. You haven't used it up to now? Okay, later you would have VDD. So, if gate, the voltage of GS is 0, and we have VDD here, then PMOS is on. So transistor would be on or off. If GS is 0, and then that would be on. If the transistor is on, it means it acts like a switch which is closed here, and it means that VDD will be here and W will become VDD. Again, I tell again. If G is 0 volt, and this is also 0, and this is 5 volt. For PMOS, at this situation, the transistor is on. So the transistor is on, means that this is like a closed switch. It will connect this point, this drain to source. So drain is VDD, so the source would be VDD also. So we have VDD as the output. And at this situation where gate is 0, the NMOS where gate is 0 and source is 0, then it means that there is no positive voltage here. This is off. The transistor is off. It means that this point is not connected to this point, which is good, is not connected, and just VDD is connected to this point, and this point becomes 1, VDD. VDD is 1. 5 volt corresponds to 1. So here you see when A is 0 volts, then W is 1. Now let's see what happens if A is 1. When A is 1, here we have 1, and again here we have 1, and here we have 0. When there is not G and S, they don't have same potential, same voltage, so this would be off. So this would not conduct. This is off. But NMOS, here we have 1 here, we have 0 here, so we have a 5 volt voltage here. So NMOS will be on, and this will conduct. This would be, the switch would be on. So it means that 0 is connected to W, so W becomes 0. So when A is 1, W is 0. When A is 0, W is 1. So what is this? This is inverter. When input is 0, output is 1. When input is 1, output is 0. So this is inverter. So we have built an inverter using 2 transistors. If you remember, whenever I wanted to count the transistor, I put 2 on inverter. And when using these 2 and you put them together, another PMOS and NMOS here, and we built this circuit with 4 transistors, we would have a NOR function. And this is why we told you that NOR is very good, because just needs 4 transistors. After the inverter, which has only 2 transistors, putting 2 of the inverters together, then we have NOR. Okay, I don't go through that detail. Maybe I already talked too much. But you saw this circuit. Now, let's see what is transistor. What is an NMOS transistor or PMOS transistor? Actually, the symbol, I will show you the symbol here. So for the building a transistor, we are using a silicon. On silicon, we put impurity like electrons or holes, and then we try to use them to build some kind of switching circuit, a switch circuit that we could control it. It becomes either on or off, as I showed you in the previous slide. But how do we do it in electronics? In electronics, here we have 2 N silicon. It means a silicon with electron impurity. It has more electrons inside it than holes. So the electrons could move here. But if we have a P impurity, it means that holes can move. So if this is the case, when this is an NMOS, if I put voltage here, this is source, this is gate, this is drain, and then if I put a 5 volt voltage between gate and source, then what happens? When I put positive voltage here, then the electrons, because it is a positive voltage, positive attracts the electrons, attracts negative charge. So the electrons come up. So here we call it a channel. They build a channel of electrons that they could move now, because here we have N, which is electrons, N electrons, and here also we have electrons coming to help them. Then the currents will be on. The current happens. A current of electrons will happen. So if you put a positive value of voltage here, then it will make a channel. The channel makes the electrons to move, and it conducts. We can say it conducts at this time. So it is on. So this is how it works. Now look at this. When we put the voltage here, the electrons are coming to charge that. So it is not instantaneous. It takes time. They have to come at that position, and then they try to move, and it takes time. And because we have delay, for sure we have delay. It is not instant. It is not like a metal switch that you press and then it is on. If you have plugs, switch here, then you press it, it is on because it has a metal. So if you press it, two metals stick together, so they conduct. This is instantaneous. But here it is not instantaneous. It takes time. And again, the same thing for PMOS, where when we put voltage and that. So transistor structure, we can see. I don't go to this detail. I already see that you are getting tired. So we have capacitance, we have resistors here, so we have some kind of RC circuit here. And from the electronics, you know that RC circuit has delay. When you put a voltage on that, it doesn't reach to 1 instantaneously. It takes time to for the capacitor to get charged, and so it has delay. So we have capacitance, we have resistance, and the capacitance is proportional to L times W. L is the length of the L is this is L, and this is W. So the capacitance is proportional to L times W, but the resistance is proportional to L by W, L divided by W. Okay, so I just told everything that I wanted to know. That's it. Now we go here. We go to the gate level. In the gate level, we just assume that there are delays here. Look at this circuit. What is this circuit? We had this before. It is a multiplexer. Do you remember multiplexer that we have taught? If B is 1, then A comes to output. If B is 0, then C comes to the output. It is a multiplexer. B is the select, and A and C are the two inputs of the multiplexer. Okay? We had this before. Let's assume that our NOT gate has a 5 nanosecond delay. Our AND gates have 7 nanosecond delay, and our OR gate has 3 nanosecond delay. So let's see what happens. Before having a delay, let me draw the timing diagram, and then using the delay, write the timing, draw the timing diagram. Okay, so let's say we have A, B, C, and also we have W here, we have X, and we have Y. So let's draw the timing diagram for this. Assume that A is 1, B is 1, C is 1. So based on the circuit, based on our design, when B is 1 and A is 1, this will become 1, W becomes 1, X is 0. Because B is 1, then V is 0, 0 and C becomes 0, and 1 and 0 becomes 1. Okay, so if A is 1, B is 1, C is 1, W is 1, X is 0, and Y is 1. Okay. Now assume that B becomes 0. So before B was 1, so we were selecting A as the output. Now B becomes 0, so we are now selecting C as the output, okay? This is the multiplexer. So C becomes 0. So C becomes 0. When C becomes 0, V is the NOT of C, so V becomes, where is V? Oh, I didn't put V. It was good if I put V also here. Okay, so let me erase V. V should be before X, so I put V here. Oh, too bad. You didn't tell me to write V. Okay, V. So when B becomes 0, why I put C? When B becomes 0, then V becomes 1 because V is not of B. So B becomes, before it was 0, now it becomes 1. V becomes 1, and then V is 1, C is 1, so X is 1. X becomes 1. Okay? But B is 0, A is 1, B is 0, so W becomes 0. W becomes 0. And C is still 1. C is 1, A is 1, B becomes 0, and this is what happens. So what would be Y? Y is still 1 because we have now X as 1, and X or W becomes 1. So Y is still 1. Okay? Anybody? Agree? Yes, please. Sure, that's what we are going to show you. This is with assumption of no delay, everything instantaneous. And this is exactly what I want to show you, that this is not true. This is not in the real world. In the real world, there happens something else, which I want to show you. But that gave you the idea that ideally, just pay attention to me, ideally this circuit in this situation should stay on 1 because A and C, both of them are 1. So regardless of B, which is 0 or 1, the output should be 1. Okay? Do you follow me? This is the function of the circuit. The function of the circuit is a multiplexer. So if this is a multiplexer and both of the inputs are 1, so regardless of the select, either it is 0 or 1, it should be 1, the output. Okay? So ideally, we would like it to be 1 at all the times. But this is something that doesn't happen. Let's see how. Now, I write it with delays. Now, we have delays on our gates, and we write it again for you. This time, I wanted to draw at the same position, but it is too complicated. So I write it down here. So again, A is 1, B is 1. No, B is not 1. A is 1, C is 1 the whole time. A is 1, C is 1, B at the beginning is 1, then it becomes 0 at some time. So let's see what happens. And then we have W, we have X, we have W, X, V, we have V, don't forget V like last time. W, V, It is really hard to draw with the finger. V, X, and Y. So let's see. A is 1, B is 1, so W is 1. Okay, W is 1. Then B is 1, so V is 0. V is 0. V is 0, C is 1, so X is 0. X is 0, W is 1, so Y is 1, because it has all of them together. Put it. Y is 1. So at this position, at this time, B becomes 0. So let's see what happens. B becomes 0. V is the knot of B with a gate, inverter gate with 5 nanosecond delay. So V becomes 1 with 5 nanosecond delay. So V becomes 1 V becomes 1, oh, not this blue, the other blue. V becomes 1, but with 5 nanosecond delay, not at the position of the yellow dot. So 5 nanosecond later, V becomes 1. 5 nanosecond later. And then so what about W? W is AND of A and B with 7 nanosecond delay. A is 1 and B became 0. So W should get 0 now, but with 7 nanosecond delay. So W, not at this time, but 7 nanosecond later becomes 0. So this is W. So V has a delay of 5 nanosecond, W has a delay of 7 nanosecond. What else? What about X? X is V and C. Before this time, the 5 nanosecond after the yellow time, nothing happened, so X is still 0. X is 0. But at this position, 5 nanosecond after yellow, V became 1. So V became 1. And C is also 1. So X should become 1. But with 7 nanosecond delay. So X is still 0 here. But at this time, with 7 nanosecond delay, it becomes, with 7 nanosecond delay, not instantaneously. So X is 0 with 7 nanosecond delay, which is, should be 7 nanosecond. After this is 5, and then we have 7. So somewhere like here. So this is 12 nanosecond after yellow. Remember, this is 12 nanosecond after yellow. So X now is 1. Let's look at Y here. Y, this is important now. Y is the OR of W and X. And we have sometimes here where W and X, both of them became 0. That's our problem. Let's say this one. Here you see W is 0 and X is also 0. So there are some times that both of them are 0, so y becomes 0. Yeah, that's the problem. But y has 3 nanosecond delay in that. So when do we have 0 here? We have 0 at this time. At this time, here w became 0, and x is also 0. So at this time, after 3 nanoseconds, which I don't know, is it before that? You should write it very carefully so to see how it works. So after some delay, let's say 3 nanoseconds of something, I have a diagram which is very good. So we will look at that later. Y becomes 0. And here it stays 0 until x gets 1. It takes time. So later x becomes 1 and then y becomes 1. This is the problem. I will highlight it with yellow. This is the problem. We didn't expect this. Y should stay 1 at all times because all of our inputs are 1. When all of our inputs, regardless of select, which is B, it should be 1, but it is not. So this is a hazard. Hazard happened. Hazard happened. Something that we didn't expect happened. A glitch happened. There is a glitch here. It became 0 and then it becomes 1 again. It returns to 1 again. But there are some times which is about 5 nanoseconds. In this case, it is 5 nanoseconds. It is 5 nanoseconds, it is 0, and then it becomes 1 again. If we do this exactly the same for when B becomes 1 again, so if you do it when B becomes 1 again, I don't do it in detail, but you do it because it is a very good practice, and we should have some kind of hazard question in the exam also in the midterm. But you should know, you should learn it. It is very a very required concept. You need to know about it. If B gets 1, then either even we have delays, then this doesn't happen. The y remains 1 at all time. It doesn't have a glitch. It doesn't get a glitch to become 0 and then back 1. So you should think about it. Why? What happened that when B from 0 becomes 1, this doesn't happen. But when B from 1 goes to 0, it happens. You think about it later. So let me show you. I should have written here. So is it okay if I erase my inks? Remember, here we draw a diagram without delay, and then we draw it with delay, and this is the result. This is the result. Okay, here you see the numbers. So after B becoming 0, 5 nanoseconds it takes to V becomes 1. V is the knot of X. And then W becomes 0 after 7 nanoseconds of B becomes 0. W is AND of A and B. B becomes 0, so W becomes 0, should become 0, but with 7 nanosecond delay. And then the delay of this with this accumulates, and after 12 nanoseconds we have X becomes 1. And since there are times that W is 0, X is 0 also, there are times because X getting 5 nanoseconds later than W, then we have glitch. This is our glitch here. Okay. So we could say something. This multiplexer, if A and C are both 1, regardless of B, output should be 1. But we see that if we make B from 1 to 0, there the glitch happens, and the delay of 2 pass. Why this happened? Because look at here, B has 1 pass to reach the output here. This is the first pass. The next pass of B is this. So in the first pass, B gets 10 nanoseconds to reach to the output. But in the second pass, B gets 15 nanoseconds to reach the output. And because they are not the same, they are different, then this glitch happened. The potential hazard, we have a potential hazard when we have different passes from one input to the output with different delays. It has a potential to become a hazard. It is a potential hazard, but we should go to the analysis of that to see if it's really the hazard is happening or not. But it is a potential hazard when you have something like that. And I told you, if you try from 0 to 1, then I showed you here, and the glitch doesn't happen. Because if you look at the diagram, you know why. Because it gets later, but it stays at 1. Okay. And let me give you some insights. So this is the shorter delay with 10 nanoseconds. This is the longer delay with 15 nanoseconds. So glitch happened. This glitch, we call it 1 hazard, because we wanted the output to be 1, but it didn't. It became 0 at one time and then returned to 1. So we call it 1 hazard. If you have a circuit which we want the output to be 0, should be 0 if there is no delay, then it becomes 1 and then comes back to 0, then it is 0 hazard. So this was a 1 hazard in this case. And the 1 hazards happens for AND OR circuits, but the 0 hazard happens for OR AND circuits. Hazards occur when moving from shorter delay, which B is 1. In shorter delay, when B is 1, then it uses this pass to make Y 1. Because B is 1, then A is 1, W becomes 1, 1 or anything would be 1, and this is the pass which B makes the Y of 1 at the shorter pass. But when B is 0, it uses this pass to make Y as 1. So hazards occur when moving from shorter delay, B equal to 1, to longer delay, which is the B0 pass. Did you get what I told you about the passes? We call this pass as B equal to 1 pass, because at this, when B is 1, that pass is important for Y, and when B is 0, the longer pass would be in effect and makes the Y as 1 at that position. Duration of the hazard would be the difference of these two passes. You see, our glitch was 5 nanosecond wide, and this 5 nanosecond is the difference between these two passes, 15 and 10. When happens, the glitch happens after, you see here, after the delay of the shortest pass, which is 10, you see, glitch starts here. And here is 10 nanoseconds after when B became 0. 10 is the shorter pass. So the glitch happens shorter pass delay after the change. Here B became 0. 10 nanoseconds later, glitch started. 10 nanoseconds later, glitch started. Okay. Now let's look at KarnoMap, and from KarnoMap, you see KarnoMap has various properties. You could have some insight from KarnoMap. From KarnoMap, I show you that you could guess that we could have a hazard here. A potential hazard could be detected by KarnoMap. You see, KarnoMap. KarnoMap of the of this example is this, the multiplexer. So this is the KarnoMap. Now what do? We map them, this, and this. These are our implicants. So if you write essential one, the essential ones would become this one and this one. The other one is not essential. So we just select this implicant, which corresponds to this, AB, and we select this implicant, which corresponds to BC naught, which is, B naught C. You see, this implicant corresponds to this gate, which builds AB for you, and this implicant corresponds to this gate, which builds B naught C for you, and that's it. We don't have any other one left, so that's it. Okay, that's it. But you see, there are two ones here next to each other, which, because they are already covered, we didn't pick the implicant of that. There are ones, adjacent ones here, and we didn't pick the implicant for that. Why? Because we wanted to make it simpler. And when we made it simpler, we didn't pick this implicant, which is, this implicant is AC, which is AC. We didn't select this term because it was enough. What we had before, it was enough. We don't need to pick that. But this is the reason that we have a hazard. So if you see two ones adjacent to each other and the implicant covering these ones is not included in your function, then there is a potential hazard. I am repeating, potential hazard. I am not saying that for sure there is a hazard, but you could detect a potential hazard and then you could investigate more to see if there is. So what to do if we don't want to have this hazard? You can also include this implicant in your function. So your function would become not optimized, but it doesn't have glitch. So the function would be this. AC is also added to your terms. Okay. Before continuing, let's go to quiz. A very difficult quiz. I put it for you this time. So you should do it in 1 minute. So it is only 1 minute. 1 minute, yeah. You should be very fast. You should be very fast. Where is the quiz? Where is the quiz? Here. Okay. So now it is available. The password is 0606. 0606. Please, it has one question and it requires you to answer it very carefully. It didn't work? Oh yeah, the time. Just a moment. Quiz setup. Timing. Now here. This one, instead of 30, we make it 40. 40, no, 50. 50. Okay. Save and close. Please try again. The password is 0606. Huh? What?
Just one question.
Just one question. Very difficult. Okay.
What's the name of this question?
Attendance.
No.
Yes.
Would the midterm cover everything up to this lecture?
Midterm? Yeah, midterm, everything up to this lecture. At the end of this lecture, it is midterm. Whatever I will tell you next lecture is for the final. Okay, before continuing, I also should tell you that I put some samples. There is a module here called exam. If you go to exam, there is a sample midterm. Actually, the sample midterm is not exactly what we have covered up to now, but it is good. You will get that. This is the sample midterm for the previous semester, so I use that. And the solution, and also I've put you, if you don't have the book, if you have the books, at the end of each chapter there are problems that you could solve, and the exam would be something like that. The exam, you don't need to memorize anything, but you need to know how to map ones in a Carnot map, what would be the De Morgan rules, something like that you should know, but there is nothing more that you should memorize. So you need to solve the problems. It is a problem that you need to solve. So you look at those questions. If you have any questions about them, you could ask in the tutorial section or from me. We have 4 minutes. Give me 4 minutes. So I told you how to solve this. There are some definitions which I would like to let you know. If you came across these terms, you know what they mean. A static hazard is what we saw up to now. A static hazard, the one we saw was a static 1 hazard, and there is also a static 0 hazard. A static 1 hazard is the output is currently 1, and after the input change, the output momentarily changed to 0, and then again coming back to 1, which should be the stable state of the output. And a static 0 hazard is the output is 0, but sometimes it gets 1 and then comes back to 0. We have also dynamic hazard. Dynamic hazard says that there are more than one changes. For example, your output should be 0, then it becomes 1, then it becomes 0, then later it becomes 1, then becomes 0, and then it is stable. So this is the dynamic hazards, and this is the static hazard, this is dynamic. Dynamic, in our case, when there is a change in only one input, in our case B, then it will generate only a static. Dynamic hazard doesn't happen. Dynamic hazard happens when there is a large circuit with different passes, with different delays, or there are two changes, two inputs, more than one input change. Then that might happen. So whatever we told you, we are covering just a static hazard, not dynamic hazard, but you know that. So what we told you here in this chapter, we tried to realize logic circuit, we saw Boolean algebra, then we used minterms, then we used Carnot maps, then we saw don't cares, then max terms, and then hazards. Okay, have a good day. So look at the questions of the book. If you have problems, let me know in your tutorials also.